Good afternoon. Today I'm going to start the new chapter called Equivalence Class Testing. This is the third chapter of second module. The first two chapters you have studied, that is pseudocode examples. Then you have studied the boundary value testing, right? And the third chapter is equivalence class testing. So in this chapter, we are going to study about what is equivalence class testing, why we are using the equivalence class testing, and you study the disadvantage or the limitations of for boundary value analysis testing, right? That we want to overcome by using the equivalence class testing. And here you are going to study about some of the equivalence class testing strategies, and you're going to study the test cases for the equivalence class testing by considering the three examples. Those you have already studied in previous chapters. Those three problems are the triangular problem, next state function problem, and the commission problem. The test cases we are considering same thing, okay, and we are applying for the equivalence class testing. Okay, so first we'll see what is the equivalence class testing, then what are the disadvantages with the boundary value, what are the limitations of boundary value analysis, then how we can overcome by using the equivalence class testing. So what is equivalence class testing? So basically equivalence class testing is used to have the sense of complete testing and to avoid the redundancy. Means in order to perform the complete testing and to avoid the redundancy, we are using the equivalence class testing, because these are the three major limitations that occur in the functional testing or boundary value analysis. What are those? One is the redundancy problem arises, and second one is the existence of the gaps when we are performing the boundary value analysis testing, that we want to overcome by using the equivalence class testing. And hence the equivalence class testing is used to have a sense of complete testing and to avoid the redundancy, because these two are not realized, are not overcome by using the boundary value analysis testing. Because so when we have considered the test cases for those three problems, we have the more number of redundancy exist, and also the gaps existed between the test cases, so that we want to avoid in the equivalence class testing. Okay, so equivalence class testing echoes the two deciding factors of boundary value testing. Those are the robustness and the single or multiple fault assumptions. Okay, so we are considering these, that is the robustness and the single or multiple fault assumptions, that we are our equivalence class testing echoes these two factors. But when we are going for the robustness or the robust forms, there are two problem arises. One is that the specification will not define what the expected output for an invalid input. So when we are defining the test cases, there we are defining the test cases for the valid inputs and the invalid inputs, right? So when we give the valid inputs, obviously we will have the expected output. But when we are defining the invalid input test cases, then for such type of inputs, it is very difficult to define the expected output. So this that problem arises when we're using the robust form, and the other one is for the strongly typed languages, because when we're using the strongly typed languages, this eliminates the need for the consideration of invalid inputs. Means whenever we are using the strongly typed languages, there we can use that only the valid test cases, and the invalid test cases cannot be considered. So these two problem arises. One is the specification does not define what the expected output for an invalid input, and the second one is for the strongly typed languages eliminate the need for the invalid inputs. So this problem arises with the robust forms. So first we'll see. So as I said, we are going to use the equivalence class testing. So to use the equivalence class testing, first you need to know what is an equivalence class. Okay. So equivalence class form a partition of a set where partition refers to a collection of mutually disjoint subsets and the union of which is the entire set. So you already studied the set theory and all right in the DMS, right? ಓದಿದಿರಲ್ವಾ what is a set and union of two sets, intersection of two sets and disjoint sets. ಓದಿದಿರಾ ರಾಘವೇಂದ್ರ, Nikhil, Suraj? You studied that, right? What is a set and what is the union of two sets? Then the intersection of sets, disjoint sets. So that a concept we are using in the construction of equivalence classes. Okay, so equivalence classes form a partition of a set where partition refers to a collection of mutually disjoint subsets. So a set, when we from the set we can form the subsets where those subsets are mutually disjoint, and when we perform the union operation on those disjoint subsets, then it leads to the entire set. So that property we're using in the equivalence classes. Okay, equivalence classes form a partition of a set where partition refers to the collection of mutually disjoint subsets, and the union of those disjoint subsets results in the entire set. So when we're using that for the testing purpose, there are two important implications. One is the entire set is represented provides a form of completeness, and the disjointness ensures a form of non-redundancy. Means, so here when we are uh, using the disjointness, that is we are constructing the subsets of a set where those subsets are mutually disjoint, and when we are using the disjointness in construction of the subsets, that forms the non-redundancy. Okay, because the subsets are determined by an equivalence relations and the elements of a subset have something in common. Okay, so subset that we have constructed from the set itself, hence they will have the something which is the common factor in different subsets. So the idea of equivalence class testing is to identify the test cases by using one element from each equivalence class. So what is the main idea behind the equivalence class? The main idea behind the equivalence class is to identify the test cases by using one element from each equivalence class. And if we choose the equivalence classes in a wise manner, then it reduces the redundancy among the test cases. Okay, the main idea behind the equivalence test class is to identify the test cases by using the element from each equivalence class. Right, when we are choosing the equivalence classes in a wise manner, then it reduces the redundancy among the test cases. Now let us consider the example of a triangle problem. So in the triangle problem, if we consider the equilateral triangle, when we say that the triangle is equilateral triangle, if all three sides are of equal length, then we say that the triangle is a equilateral triangle. So if we consider the value as 5 comma 5 comma 5 or 6 comma 6 comma 6 or 100 comma 100 comma 100, what this 100 comma 100 comma 100 comma 100 indicates? These are the sides of a triangle. If you consider sides of the triangle as A, B, C, then A value is equal to 100, B is equal to 100 and C is equal to 100, like that. Okay. So here, if we consider 555 or 666 or 100, these are all the different test cases that we are formed that we are constructed in the boundary value analysis. See here the redundancy occurs because all three are the examples for a equilateral triangle. And if here we can consider any one of the test case, and that will be considered as the equivalence class, and that will be used for testing the implemented program. Okay, so here these are the redundant, and if we consider all these as same, and if we consider one test case, and by eliminating the remaining two test cases, we can eliminate or avoid the redundancy. Understood? Okay. So similarly for the isosceles triangle, if we consider when we say that the triangle is isosceles triangle, if any of the two sides are equal, then we say that the triangle is a equilateral triangle. So if we consider the example like this, the sides of a triangle as 10 comma 10 comma 5 and 20 comma 20 comma 6, 20 comma 20 comma 5, then 100 comma 100 comma 5. So here what happens, in all three test cases the two sides are equal and the third one is different, and all three test cases are examples for a isosceles triangle. In such cases we can treat the all as the same, and we can eliminate the other two test cases so that we can avoid the redundancy. So that is happening only through the equivalence class. Why? Because here in the equivalence class testing we are considering the test cases which are same, and we'll eliminate the uh, test cases which are same, and we'll consider only one test case. So in this way we are eliminating the redundancy. So now let us consider an example of a function with two variables x1 and x2, uh, where x1 and x2 will have the boundaries, because for each variable we are defining the boundaries. Here you can consider, you can see the example. Here we have the two variables for the function f. F is a function with two variables x1 and x2, and the input variables x1 and x2 will have the boundaries. Here you can see that a less than or equal to x1 less than or equal to d. What it indicates, the x1 is having the boundary from a to d. Similarly x2 is having the value ranging from e to g. So the values which ranging between a and d are the valid inputs, and the values outside the range a and d are treated as the invalid inputs. Similarly for x2, the values are ranging from e to g, e less than or equal to x less than or equal to g, which indicates that the range for x2 is from e to g, or the value of x is varying from e to g. Whatever the values resides within the range e to g, then we are considering them as the valid inputs and the other as the invalid inputs. So for the first variable x1, the intervals are also given like this, a comma b. See the difference here. We have the square bracket and the parenthesis, square bracket and the parenthesis. Finally, it is the square brackets. So what they denote? The square brackets denote the closed interval endpoints, whereas the parenthesis indicates the open interval points. Okay. So here for the x1 we have the uh, square bracket as well as the parenthesis, right? So the square bracket indicates the closed interval endpoints, whereas the parenthesis indicates the open interval open interval endpoints. And so this is the test cases constructed for the equivalence class. So here, as I said, we have two variables x1 and x2, where the x2 is ranging from a to b, where and x1 is ranging from a to b, and x2 is ranging from c to d. And whatever the test cases will consider within this range are the valid inputs, and others are the invalid values. See here they have given. Check this here. See, the range between C and D is considered as the valid values of x2, and outside D and C are considered as the invalid values of x2. See here in the graph it is represented invalid values for x2, and here also it is invalid for values for x2. Similarly for x1 range is given, right, a to b. The values ranges are resides within this range are treated as the valid values, and outside this range is treated as the invalid values. See here, before a all the values are treated as the invalid values for x1. Similarly after b, the whatever the values, those are treated as the invalid values for x1. Right. So here within the range we are considering it as the valid values. Outside the range we are considering it as the invalid values. So invalid values of x1 and x2 are x for x1 it is a x1 which is greater than d, and for x2 it is e x2 which is greater than sorry e x2 of g. So then we will have the invalid values. See here, the commission ranges in the commission problem are equivalence classes. So here, if we consider A, B, C, D are the values within the range of x1, and whatever the test cases resides within this range are treated as the valid values. So similarly, for x2, we are considering three values E, F, G, and the test cases which resides within this range are considered as the valid values or valid input values, and outside that are treated as the invalid input values. This is over, right? Hmm. So let us consider the with the help of this graph we can identify with this graph we can identify what are the valid values and invalid values. See here, five values are defined. Five valid values are defined: v1, v2, v3, v4, and v5. So for v1, if we consider x1, for x1 a less than x1 or less than b, that is treated as the valid one. Why? Because see here, the values are within the range. For x1 it is a less than or equal to x1 less than or equal to b. Okay, so this is considered as the valid value because the value is between the range a and b. Similarly, for v2 where value 2 and b less than or equal to x1 less than c. So here, see here, in this case it is a to b, b to c, and c to d. All are treated as the valid input values. See here, so one is from a to b and the other one is from b to c and the one more is from c to d. All three we are considering as a valid input cases, right? So v1 which is ranging from a to b, and v2 ranging from b to c, and v3 is ranging from c to d. Similarly, v4 and v5 we are considering it for x2. So for x2, if it is ranging from E to F, that is the valid case that we are treating it as a V4, and one more is from F to G that we are treating it as the valid value V5. So all the five values that we are treated as the valid input cases are the valid input values. Okay, similarly, we'll consider the invalid values. If x1 is less than a, what happens here? So x1 is ranging from a to d, a to b, b to c, and c to d. Outside this value or outside the d, x1 is treated as invalid. See here, x1 value is starting with a. Whatever the values less than a is treated as the invalid value, and whatever the values greater than d is treated as the invalid value for x1. Similarly, for x2, whatever the values less than e is treated as the invalid one, and whatever the values greater than g is treated as the invalid values. So these are defined here. NV1, NV2, NV3, and NV4 indicates the invalid values. Okay, for x1 is less than a, that is the invalid one, and if d is less than x1 then also it is invalid, and if x2 is less than d or g is less than x2 then such type of values are treated as invalid values. Now we have the equivalence classes: five valid equivalence classes and four invalid equivalence classes. If you see the values, if you consider this as the set, see the subsets are the elements of these sets or these subsets. So there is no common element in each of these sets, right? Here we have the A, B, B, C, C, D, E, F, and F, G. Similarly, here it is less than A or greater than D, less than E and greater than G. right? No common elements exist in these sets, and hence when we perform the union of these sets, v1 v2 v1 union v2 union v3 union v4 union v5 union of n v1 union nv2 union nv3 and nv4, then this results in a entire set. Okay, that I explained in the last slide, right? So when in the equivalence classes, what we are going to do, we are going to construct the subsets where these subsets are mutually disjoint, and when we perform the union operation on these mutually disjoint subsets, then it results in a entire set. Okay, next we'll consider the another form of the equivalence class testing called as the weak normal equivalence class testing. In the weak normal equivalence class testing, the class testing is accomplished by using one variable from each equivalence class in a test case. So here we have constructed the number of test cases by using the different values of x1 as a b c d. Similarly for x2 e f g we are considering, right? So when we use these and the the values, when we choose within this range, we will have number of test cases. So but to perform the weak normal equivalence testing, we will choose one variable from each equivalence class in a test case. Now let us consider this as one test case, this is another test case, and this is another test case. So for this we'll consider one variable a between A and B and between E and F. Similarly, for this it is between B and C and between F and G. And similarly for this it is between C and D and F and E. Right. So here we are considering the test cases which uses one value from each equivalence class. The test case here, the test case in the lower left rectangle corresponds to the value of x1 in the class A and B. Why we are represented it as square bracket, starts with square bracket comma A comma B open parenthesis, right? So this indicates that square bracket indicates it is the closed value and are the closed variable, and B indicates that it is open. Why B is indicated by the open? Because the value of B is extended up to C and from C to D. But for A is the that is the minimum value that we are considering for the x1, and beyond that or less than value of a is treated as the invalid input. Okay, that's why the value a is treated as the first minimum value for x1, and b is treated as the open variable. Why? Because the value of b can be extended up to c or up to d. So hence the test case in the lower left rectangle corresponds to the value of x1 in the class square bracket of a comma b and the parenthesis, and the value of x2 in the class is e and f. Here e and f, where e is represented with the square bracket and f with the parenthesis. This indicates that a e is fixed and f value can be extended or changed up to a g. Right? Understood? Similarly, if we consider the test case, one more test case, here it is, one more test case here. So between C and D, one more test case is there. Right. Then what will be the value for this? Okay. So what will be the value for this? For the test case that is in the this particular rectangle corresponds to the value of x1 in the class parenthesis C comma D square bracket. Why C parenthesis? Because C can be decreased from to B or to A, and hence for C it is parenthesis, and D for D it is a rectangle. Why? Because after D we can't increase the value of x1. If we increase the x1 value behind D, then it leads to the invalid test case or invalid input case. So that's why we are not considering that. Similarly, for this test case, what we can have here, both B and C are the parentheses. Why? Because B can be extended up to C and C can be extended up to D, and hence B, C are represented with the parenthesis, whereas FG values are represented with the parenthesis and the square bracket. For F it is the parenthesis and for G it is the square bracket. Why? Because that is the end value. G is the end value for x2. Behind G we cannot increase the value of x2. If we increase that, then what happens? It leads to what? The invalid input. Okay, understood. Weak normal equivalence test cases. Any doubt in this? Yes, Suraj?
No, ma'am.
Okay. Understood, right? Weak value equivalence test classes. Okay. Weak normal equivalence class testing, that you understood, right? Any
Yes,
doubt?
ma'am. Yes, ma'am.
One more, Nikhil. Nikhil, any doubt? Okay, next we'll move on to the strong normal equivalence class testing. Next one is the strong normal. ಯಾರು ಆ ಕ್ಲಾಸ್ ಮುಗಿದ್ಮೇಲೆ ಇನ್ನೊಂದು 10 ನಿಮಿಷ ಇನ್ನೊಂದು ಕಾಲ್ ಗಂಟೆ ಅಂತ ಹೇಳಿ. ನೆಕ್ಸ್ಟ್ ಒನ್ ಈಸ್ ದ
No, ma'am.
ಸ್ಟ್ರಾಂಗ್ ನಾರ್ಮಲ್. ಹಲೋ ಹಲೋ ಸೂರಜ್ ಹೇಳಿ. Next one we have the strong normal test equivalence class testing. So first you studied the weak normal equivalence class testing. Next we'll consider the strong normal equivalence class testing. And the strong normal equivalence class testing is based on the multiple fault assumption. So test cases from each element of the Cartesian product of the equivalence class is considered. So when you compared with the weak normal equivalence test cases, there the number of test cases are less. You can check it here. Here we have only 3 test cases that we have considered for the weak normal equivalence class testing. But in the strong normal equivalence class testing, we are considering all possible test cases for each element in the each element of the Cartesian product. Okay, so here for the strong normal equivalence class testing, we are considering the test cases from the each element of the Cartesian product. Right, understood? And when we are performing the Cartesian product on the different test cases, then it leads to the completeness of the testing. Okay, so because the Cartesian product guarantees the completeness. So see the difference between weak normal and strong normal class testing. In the weak normal class testing, we are considering the limited number of test cases, whereas in the strong normal equivalence class testing, we are considering the test cases from each element of the Cartesian product. If we consider this as one element of the Cartesian product, this is another element, this is one more like this. How many elements we have? 6 elements of the Cartesian product. So we are considering each element of the Cartesian product of the equivalence class, and that we are using it for the strong normal equivalence class testing. So when we choose the elements from the Cartesian product, it guarantees or it assures the completeness. So that is the difference between weak normal and strong normal. So the major thing in the strong normal case is we are considering all the test cases that are chosen from the each element of the Cartesian product, because here we will have the multiple fault assumptions, and we'll choose the test cases from each element of the Cartesian product. Understood? Why we are choosing like this? Because it leads to the, or it assures the completeness. So this is about the strong normal equivalence class testing. Next we'll move on to the weak robust equivalence class testing. So here we have the 2 words, right? Weak and robust. So if it is weak, can we say that it is robust? Or if it is robust, can we say that it is a weak testing? No. So hence we'll combine both weak, robust, and we'll have one more equivalence class testing strategy called as weak robust equivalence class testing. Here the robust part comes from the consideration of invalid values, and the weak part refers to the single fault assumption. Understood? So here we are considering the two parts. One is the weak and the other one is the robust. So the robust part comes from the invalid values, whereas the weak part comes from the single fault assumption. So invalid values means the values which resides outside the range. So for x1, what is the range? Range is from A to D. And outside A and D value is considered as the invalid value. Similarly, for x2, it is between the value E and G, then that value is treated as a valid value. And outside the range, E and G is treated as the invalid value. Okay, see here, you can see this. The weak robust equivalence class testing considers the combination of the single fault assumption test cases and also the invalid values. See here at the left uppermost corner we have the test case. See here, this value, this is the example for an invalid value. Similarly, here it is lowermost right corner value, this one, this value is the invalid value. So for the robust testing we are considering the invalid values, and for the weak testing we are considering the single fault assumption values. So these three which resides within the range, see here, this value and this value belongs to the weak equivalence class testing, whereas the these two values belongs to the invalid value, and that we are taking for the robustness testing. Okay, hence weak robust equivalence class testing consisting of two parts. One is the weak part and the second one is the robust part. Robust part comes from the consideration of the invalid values, whereas the weak part comes from the single fault assumption, right? So, what is the process for the weak robust equivalence class testing? The process of weak robust equivalence class testing is a simple extension of weak normal equivalence class testing, because we are picking the test cases such that each equivalence class is represented. Okay, so the weak robust equivalence class testing is simply the extension of a weak normal equivalence class testing, because we are extending the weak normal test cases to the robust values, because in the weak normal we are considering the fault assumption test cases, but for the robustness we are considering the invalid values. And the process for the weak robust equivalence class testing is similar to the boundary value testing process. Here, for the valid inputs, we'll use one value from each valid class, and for the invalid inputs, a test case will have one invalid value and the remaining values will be valid. See here, if we consider this, here this is the invalid value. One is the invalid value and the remaining are the valid inputs. Or if you consider this case, this is the invalid value and the remaining three are the valid one, like that. Okay. So for the valid inputs, we'll have use one value from each valid class, and for the invalid inputs, we'll consider the test cases that have the invalid value and the remaining values will be the valid one. So if else, so if we consider a single failure should cause the test cases to fail. Why? Because if we consider the invalid inputs, what happens here? If this is the invalid input or this one is the invalid input. So if we consider the invalid input, what happens to the testing process? The testing process leads to the failure of the test cases. Why? Because there we chosen the invalid inputs, right? So hence a single failure should cause the test cases to fail. Why the test cases will fail? Because we are considering the invalid inputs. Okay, whenever we consider or choose the invalid inputs for the test cases, obviously that leads to the failure of the program or the system. If system fails, then that leads to the failure of the test cases. Okay, so hence there is a potential problem with these type of test cases. As I said, we will have the upper left or the lower right corner values. So these are these two cases. If you consider these two, the problem arises because each of the test cases represents values from two invalid equivalence classes. See here, these two. For these two, we have the two invalid equivalence class. This is the invalid one. This is the invalid one. Two invalid equivalence test cases arises or exist, and the remaining three are the valid equivalence test cases. So hence the problem arises. Whenever the invalid cases occurs, then the system leads to fail. If the failure occurs, then we say that it is the failure of the test cases. So each failure of either of these two test cases could be due to the interaction between the two variables. Then we can have the compromise between the pure weak normal equivalence class testing and its robust extension. See here, this is the revised weak robust equivalence class test cases. So here we have the valid test cases. Along with that, we are considering the invalid one, and when we are considering the invalid one, we need to define the ranges. Okay. So this is the revised weak robust equivalence class testing. So next we have the strong robust equivalence class testing. So then what is the difference between weak robust and the strong robust case? So in the weak robust case, we are considering the minimum number of test cases, valid test cases and the invalid test cases. When we choose the valid one, we are considering the single fault assumption, but in the strong robust equivalence class testing, we'll consider the multiple fault assumption values. And also, so here once again we have two parts, strong part and the robust part. For the robust part, we are considering all the invalid values. Similarly, for the strong part, we are considering the multiple fault assumptions. But in the weak robust, what happens? We are considering the values with single fault assumption and with a minimum number of invalid cases. But in the strong case, we are considering the multiple fault assumptions and also the more number of invalid values. See here, in this case, see here, we have more number of invalid test cases for each equivalence class. See here, if this is one equivalence class, this is another one like this, and we are considering more number of invalid values. Similarly, we are considering the more number of multiple fault assumptions. So test cases from each element of the Cartesian product of the equivalence classes are both valid and invalid. How we have taken this, both the valid and invalid classes, we have taken with the help of the Cartesian product of all the equivalence classes. So when we perform the Cartesian product of all the equivalence classes and we take the values, then that leads to the completeness, or that assures the completeness of the testing. And hence, in the strong, robust, or the strong normal equivalence class testing, what we are considering the multiple fault assumptions, and we'll choose the elements by using the Cartesian product form. Why? Because that leads to the or assures the completeness of the testing. So this is about the strong, robust equivalence testing. So in the next class, you are going to study about the equivalence class test cases for three different problems. There we are considering the problem of triangle problem, next date function problem, and also the commission problem. For all these three problems, we are going to construct the test cases by using the equivalence class testing. Understood? Any doubt in this? So today you have studied about what is equivalence class testing, why do we require the equivalence class testing. Then to perform the equivalence class testing, first the important thing is we need to construct the equivalence classes, and how to construct the equivalence classes that you have studied, and the strategies of different strategies of equivalence class testing. One is the weak normal equivalence class testing, and second one is the strong normal equivalence class testing. After that, you have studied the weak robust normal equivalence testing and the strong robust equivalence class testing. So these four strategies you have studied in this class. In tomorrow's class, we'll consider the test cases for these strategies. Any doubt here? Yes, Nikhil, Suraj, any doubt?
No, ma'am.
Okay, in the next class, you are